I'm mixing two clear things.
Okay.
I have two liquids, and I mix them, and there's no neutralization, so I pour them together. Here we go, into one thing. And so this has magnesium ions and chloride ions floating around, and this one has sodium ions and sulfate ions floating around. And when I mix them together, I just have all four of those ions floating around. There's no actual reaction happening.
Okay.
There's no change. Oh, what did I write? Sodium 2, sorry.
Okay.
Plus sulfate 2 minus. There we go.
All right.
So that can happen. Everything's soluble before and after. And so for whatever test, I would give you a solubility table, or that kind of information would be given in the problem if you did not have a table.
All right. Thank you.
Yeah.
On the worksheet, when it says include the states, it's only going to be aqueous or solid, right? Unless noted.
Well, actually,
Too.
liquid. The ones that don't cancel out, don't cancel liquid, solid, or gas.
How do we know if it's a liquid or a gas?
Okay, so the solid's going to come from the solubility table, like you mentioned. The gases may come from a gas-forming reaction. And so for those, you have to memorize. The liquids will typically come from an acid base. Neutralization, like we just did up here. Memorize, when I form H2CO3 aqueous, so acids are always soluble. This thing decomposes into water, liquid, and carbon dioxide gas. So actually you get a liquid. The gas forming gives you a liquid and a gas at no extra charge. This is actually a side reaction. You're going to form this one by double displacement, and then it's going to decompose. Technically, it's called a tautomerization. The point, these forms, water and carbon dioxide, are lower in energy. This is a more unstable form, and so it will just spontaneously break it. Technically, it gives off a small amount of energy when it does that. So let me show it in the context of a net ionic equation. H2SO4 plus sodium hydrogen carbonate. You form this, it's forming from, your choices are an acid plus a metal carbonate, or an acid plus a metal hydrogen carbonate. They're both going to end in the same place. Has anyone ever mixed baking soda and vinegar? Most people have baking soda and vinegar at home. Okay, so he's got Mickey's vinegar and baking soda. Oh, okay, cool. He's going to let it boil over. I don't know if as a kid, you guys would do, as a science experiment, a simulation of a volcano. And this is actually typically the active ingredients that makes your volcano erupt. It's taking too long. Come on, hurry up. Okay, there's vinegar. Okay, now let's add the baking soda. The suspense is killing me. Oh, it's coming. Right there. Okay, pours it in. Instant gas forming. Okay. There you go. All right, that's the video. So you guys can do that at home. Wear your safety glasses. All right, so let's do a reaction that's similar to that. So I have baking soda, but instead of vinegar, I have sulfuric acid. But essentially, it's the same kind of situation. Now, break it apart into ions. What are the ions here? What are the ions from sulfuric acid? Actually, we did that one already, right?
The two hydrogens.
2 hydrogen ions plus sulfate. Okay, good. Ah, tricky one. What does this break apart into?
Sodium.
Good. Sodium, metal, and hydrogen carbonate. Remember when we talked about naming, if I have an oxo anion with 2 minus or a 3 minus, I can add H plus to it, and I add hydrogen to the name. So let's do some naming too. So this one is simply called hydrogen carbonate. In older books, they call it bicarbonate. But this is in the modern naming system, we just add hydrogen to the name, right? Okay. But that's it. All right, so who goes with who? Who goes with who?
The hydrogen with hydrogen carbonate.
Good. Perfect. And the sodium with sulfate. So what are my products going to be? How will sodium and sulfate go together?
2 NAs.
So
SO4.
Na2, SO4. That's perfectly correct. Okay, how will hydrogen and carbonate go together? Let's not worry about that coefficient. It's +1 and -1. So what's the only way they could go together? Somebody?
Is it H2CO3?
That's correct. All right. So this is my skeletal equation. And so even though I want to break that apart, I don't want to break it apart yet because this thing is not balanced. I mean, like there's 2 sodiums in 1, there's like 3 hydrogens there and 2 there. So let's actually go and balance this thing, okay? I guess I leave spaces here like to balance. It's kind of a habit. All right, so I want to break this apart. I know this thing's going to undergo a reaction, but I need to balance it first. So at first I'm going to look here. I have 2 sodiums and 1 sodium there, so I'm going to put a 2, right? And then let's see. So I have, oh, look at that. So let's see. I have 1 sulfate, 1 sulfate, 2 sodiums, 2 sodiums. How many carbonates are here?
2.
Yeah. How many are over here?
1.
Uh-oh. I better. So before I go messing around with the hydrogens, let's balance the carbonates. And let's see what happened here, actually. How many hydrogens are here? Because, well, stop. Before I do that, okay, so I get 2 sodiums, 2 sodiums, 2 carbonates, 2 carbonates, 1 sulfate, 1 sulfate. Yeah, so it's time to do hydrogens. Okay, so how many hydrogens are here?
2.
2.
2 here, and then
3.
I have, there's
2.
2 more there. So I have 4. How many hydrogens are here?
4.
This thing's balanced, okay? Yeah?
Yes.
Okay. So now, so wait, side reaction. if H2CO3 goes to H2O plus CO2, what are two H2CO3s going to go? This one's actually the hardest one of these I could do. It's got all of it in it. So I have two, right? I have two hydrogen carbonates. So if I put a 2 here, then I'm going to get 2 waters and 2 carbon dioxides, yeah?
Yes.
So I'm going to replace this with this. So the thing, you probably will hate doing these ones because, gosh, I got to keep rewriting it. Like, what a pain. H2, I'm complaining, huh? H2SO4 plus 2 NaHCO3. Those are my reactants. Goes to, I'm going to keep the Na2SO4 plus 2 water plus 2 carbon dioxide. Okay, I know the states of these. What's the state of the water?
Liquid.
What's the state of carbon dioxide?
Gas.
Good. What's the state of sodium sulfate? Actually, we saw that from a previous problem, didn't we? That one's going to be aqueous. Sodium's always soluble. And actually, these were both given to us as aqueous, but acids are always soluble, and that has sodium in it also. So aqueous, aqueous. Okay, that is my balanced equation. Can I put that up here? Balanced. Eq. Let's do the total ionic equation. I'm going to do it faster, like we said. So this is H2SO4. It's 2 hydrogen ions, aqueous, plus sulfate, 2 minus aqueous, plus, now it's 2 sodiums, plus aqueous, plus 2 hydrogen carbonates, aqueous. You got to do that when you got to, okay, sorry. It's my bad habits. I hope you guys don't mind. And then this one's also aqueous, so that gets broken apart. 2 sodium plus aqueous plus sulfate, 2 minus aqueous. Gosh, I hardly had, you see this, I kind of gonna have room on the paper here. I better write like medium sized or smaller. 2 water, liquid, plus 2 CO2 gas. Sodium, sodium, they're both aqueous, gone. Sulfate, sulfate, they're both aqueous, gone. And then, oh, can you guys see, now with what's left, what am I gonna do with what's left here? You guys see a problem here?
Common denominator.
Common denominator. So let me strike that out in green. 2, 2, 2, 2. So the net ionic equation is when a hydrogen ion aqueous finds a hydrogen carbonate aqueous, it will form water, liquid, and CO2 gas. So that's this one. The other case would be just a little different. The other possibility for the net ionic of this would be 2 hydrogen ions plus carbonate goes to water, liquid, plus CO2. So that would be if I had like a metal carbonate, like sodium carbonate or calcium carbonate, where there's no hydrogen tagging along with it when it breaks apart. This is the one we just did, right? Okay.